Okay, so one of the things that you're learning about this week are rational equations. And I know for some people it's a lot easier to understand them when you actually have a use for them or you understand why you're learning about these, how it could be useful. So I wanted to do a video on the different applications, the most common applications of rational equations. So that way you see where these are used, how you solve them. So first off, what is a rational equation? So if we go back to the definition of rational and specifically rational numbers, those are numbers that can be written as fractions. So when you apply rational to expressions, those are expressions involving fractions, and specifically our variables are in the denominator. If you have a variable in the numerator, you can still call it a rational expression, but the techniques for solving are not necessarily the same. It's a lot easier to solve. So we look at specifically the ones where your variable is in the denominator. And then it's a rational equation when you have an equation that involves fractions with your variables in the denominator. So that's the key, is what makes it rational is you've got a fraction, and then with expressions or equations, the variable is in the denominator. So the common situations where you'd have something like this would be for ratios and proportions. So let's say you have a recipe and you need to modify it based off of a different serving size, like you're doubling the recipe or something like that. Unit conversions can be solved this way. Our percent calculations you can do using rational equations, and anything with sort of mixtures, which usually involve percents. And all of these ratios, these proportions, these all get set up the same way as a proportion. Then there are two additional types that you commonly see, which are rate equations. There's the uniform motion type, where you're using the equation d equals rt. And then there's rates of work. In real life, usually this is with machinery. There are people whose whole job is to optimize like a plant. You have different equipment, they work at different rates to try to get the optimal speed and maximize your production. The equations you would set up would be set up this way, because usually you have different equations, different machines working at different speeds. Maybe an older model is slower than the newer model. And so these are all rates of work problems where you're looking at how fast somebody works, and you try to determine how long is it going to take maybe two people working together to get this job done, or maybe five people working together, things like that. So the basic steps for solving rational equations. First step is to write your equation. And when we have applications, the equations aren't given to you. So that will be our first step, to write the equation. But then once you have that equation, you factor your denominators. Now, for all of the applications that we have, we're not going to have complicated denominators, so we won't need to do any factoring, because basically you'll have denominators that are pretty simple. But if you have rational equations that are not word problems, generally you'll end up with something with like a quadratic in the denominator, so you have to factor everything. You need to always determine what values are excluded from the domain. Basically, any number that makes the denominator 0 is not allowed, because we can't divide by 0. And that applies for regular rational equations and for the word problem types. You always need to make sure your denominator is not 0. You want to identify the least common denominator. Basically, what is that common denominator that we would have for our fractions? Then you multiply both sides of the equation by that common denominator. When we have proportions, this is basically cross multiplying, but when you have things that are not proportions, it's a little more complicated. That step 4, is going to eliminate all of the fractions in the equation. And then from there, all you have to do is simplify and solve. If you end up with a quadratic, you use it using our techniques for solving quadratics. If you end up with something linear, you use your techniques for solving linear equations. And then your last step is to, out of those answers you got, make sure that the ones that are not allowed are not part of your answers. So you need to double check your answers against the values that you can't use. So the values that are excluded from the domain, because those are the ones that you are not actually valid solutions. So we're going to be following this process through all of these word problems that I do. The word problems are going to be simplified versions of the sort of things that you'll see that are not in context, but it's using basically the same techniques. And so these are almost easier than some of the other rational equations that you would be solving. So I'm going to start with a whole bunch of word problems that are set up using proportions. And these are the easiest to solve because to solve proportions, you multiply your diagonals together. So we've got first example, and unfortunately my setup here, these are supposed to be like you're basically filling in fractions here. I was supposed to try to write a fraction equal a fraction, but it didn't quite display as I had hoped. But we have a 6-ounce box of candy, which has 350 calories. And then we want to know how many calories a 10-ounce box contains. So this is a proportion. When you're comparing, you have some set of information, and then you're using that same ratio or proportion for something larger or smaller, and you're assuming that it's going to have the same mix of candy, or this, it's going to kind of be the same, just in a larger size. It's going to change proportionally. That's where we set up a proportion. So the proportion is basically two fractions equal to each other. And so we fill in what information we have for the first fraction. So the first sentence that says that we have 6 ounces is 350 calories. So I'm going to just fill that in. That is your first fraction, is the given information. Now, the way the proportion works is that you have to match your units going across. So on the right side, I have to have ounces over calories because I need to make sure that my units match going across. So the second sentence says how many calories. So we don't know calories, so that's going to be our variable. You can use any letter you want, but typically we use X. And then we're given 10 ounces. So this is our proportion, and this is the equation that we're solving. If we leave off the units, we have 6 over 350 equals 10 over X. So that is the setup. And when you have a proportion like this, we cross multiply. So you multiply one diagonal together, and that gives you your left side of the equation. So 350 times 10. And then you multiply the next diagonal together. So that would give us 6 times X. And that gives you your right side of the equation. So we cross multiply to solve a proportion, which is basically you multiply the diagonals, and then you have to have an equal sign in between these. So this gives us an equation that then we can solve for X. So 350 times 10 is 3,500. And then that equals 6X. And then to solve for X, we're going to divide both sides by 6. So I'm going to grab my calculator here. And this gave me a decimal value. So for real world problems, we usually use decimals because we don't really do fractions in the real world as much as we do decimals. So when I divided this, I got 583.33 repeating. So if we use one decimal place, we can do 583.3. And then this is the approximately equal sign, meaning that you rounded, equals X. And our units here are calories. because that is what we're looking for, is how many calories a 10-ounce box would contain. Now, once you get your answer, you want to make sure that it doesn't make your denominator 0. So going back to our original equation, we had x in the denominator, and that is, the denominator is not equal to 0. So we couldn't get a value for x that would be 0, or that would cause us a problem. 0 calories wouldn't make sense in this situation anyway, so we don't really have to worry about that so much here. But our answer is valid because it's not equal to 0. It's an actual value. We're not going to get 0 in the denominator. And so that is your answer. Now, when you're entering this into ALEKS, you're going to need to pay attention to whether it tells you to enter it as a fraction or an exact answer. If you see the word exact, that indicates that you're going to be doing a fraction if necessary. We generally never do, I can't spell necessary. We never do mixed numbers. It's just we don't use those very often, so you wouldn't be doing it as a mixed number. ALEKS, if they want you to do it as a decimal, they'll tell you how many decimal places to use, so you want to make sure that you're rounding appropriately. Are there any questions? Okay. So there's a whole bunch of proportion problems here. Yellowstone National Park in Wyoming has the largest population of free roaming bison. To approximate the number of bison, 200 are captured and then tagged, and then they are left free to roam. Later, a sample of 120 bison is observed, and 6 of them have tags. Approximate the population of bison in the park. So this type of problem is often referred to as a capture and release or a tag and release problem. And this is actually something that is really done in biology, where you try to get an estimate for the total number of animals by tagging a certain number and then capturing some later and figuring out the proportion. And you make the assumption that the proportion of tagged in your sample is going to be the same proportion out of the total population. So this is a very common thing that actually does happen in environmental biology fields, anything where you're kind of dealing with wildlife and you're trying to estimate how many you have. So, you know, I don't think anybody here is majoring in one of these things, but it is something that actually happens. So the way that you're set up here is that you generally have the number tagged out of your total. That's sort of how you're looking at. And first you have how many tagged out of the whole population, and then you have your sample. So one side will be the whole population, and then the other side is going to be your sample. And so that's how this setup works. So first off, we captured 200 and tagged all of those. So 200 out of the total population of animals are tagged. We don't know how many bison they are total, but we know we tagged 200 of them. Then we picked a sample. We captured 120 bison. So that's the total that we captured, and of those, 6 of them were tagged. So notice that I have the tagged kind of going across from each other, and then the totals going across from each other. So you're lining up across the things that go together. So this is our setup. And we have a variable in the denominator, which makes it a rational equation. And that's x in the denominator. The denominator can't be 0, so x is not allowed to be 0. 0 would mean that there's 0 bison in the park. So we know we're not going to get 0 anyway. It's kind of silly to even think about that because it doesn't make sense, but that is part of the process here, is making sure that your denominator is not equal to 0. So we are going to cross multiply. So it doesn't matter which diagonal goes first. So 200 times 120. And then you have your equal sign, and then you have your other diagonal, which is x times 6 or 6 times x. So this gives you an equation that then you can go on to solve. So first we're going to do 200 times 120. And I just entered into my calculator missing a 0. So you always want to double check you're entering it in the calculator correctly. That gives me 24,000 equals 6x. Then I'm going to divide both sides by 6. And this actually does give us a whole number. We get 4,000. So based off of the proportion, we're estimating that there are 4,000 bison in the park. So there may not be exactly 4,000. This is just a way that we use to estimate the population. So this is used to estimate, like if you think of endangered species, how many are left in the wild. They'll do something like this. They'll try to capture some of them, tag them, and then do this calculation to estimate how many are actually out there in the wild. Moving on here, so this is also set up as a proportion, but this is specifically a rate type of proportion where you're involving sort of, you're kind of thinking about it in terms of your speed, and you're not really, it's not necessarily as clear that it's a proportion as maybe the other ones. So Pam drives her hybrid 243 miles in city driving on 4.5 gallons of gas. If she, at this rate, so basically using the miles per gallon, that's the rate, how many gallons of gas are required to drive 621 miles? So whenever you're doing some sort of comparison, you're giving some sort of information, and then you're trying to use that information to find something else, it's generally always going to be proportion. So we have 243 miles on 4.5 gallons. And generally we use miles per gallon, which means miles over gallons. So the word per means divide. So when you think of your mileage, miles per gallon, it's going to be miles over gallon. So how many gallons of gas? So we don't know the gallons, so we have to make sure that our X is across from gallons, because that's what we're looking for. And this is required to drive 621 miles. So you want to make sure that all of your units are lining up straight across. And then you multiply your diagonals in order to solve this. And again, because we have X in the denominator, we can't get an answer of 0, which doesn't make sense in this situation anyway. So I seem to be alternating which diagonal I circle. It really doesn't matter. So 4.5 times 621, and then your other diagonal, 243 times X. So calculator, 4.5 times 621. I had 2,794.5 equals 243x. So we divide both sides by 243. And we get 11.5 equals x. So we didn't get 0, which is good because 0 wouldn't make sense. So the question says how many gallons of gas. So this is the gallons of gas. In order to drive 621 miles, assuming that Pam's driving the hybrid the same way, she would need 11.5 gallons. It's always good practice to include your units there. Are there any questions? Okay. This one's a little more complicated, but it's still set up with a proportion because we have a ratio. So for a recent Congress, there were 10 more Democrats than Republicans in the US Senate. This resulted in a ratio of 11 Democrats to 9 Republicans. How many senators were Democrat and how many were Republican? Of course, this is assuming that there's no one that's of a third party. You know, these are just made up numbers, but we can do this the same way. So anytime you see the word ratio, that's telling you you're going to have a proportion in order to solve this. So let's ignore the first sentence where we have 10 more Democrats than Republicans. And let's look at the ratio. We have 11 Democrats to 9 Republicans. So I'm going to just use 11D and 9 Republicans. So I'm just going to put in D and R for Democrats or Republicans. So I'm just putting that ratio there because that's what I know. Now let's go back to that first sentence. There are 10 more Democrats than Republicans. We have to translate that into an expression. That means you have the number of Republicans and then there's 10 more. So if we use R for Republicans, we're adding 10 more. And then on the bottom, we don't know how many number of Republicans we have. We just know that there is some number. So if I erase my sort of units there, if R is representing Republicans, we know that the Democrats are 10 more than the number of Republicans. And so our ratio is set up with this R plus 10 over R. So you can see that this is slightly more complicated than what we've been doing because we don't have a number on that top right like we've been doing. We now have an expression, we have a plus going on here. Now we still have to worry about the denominator that can't be equal to 0. So we can't have 0 Republicans, which we know we're not going to have. So we don't really have to worry too much about it. So cross multiply 11 times R. So that's 11R equals 9 times R plus 10. So when you multiply by the R plus 10, you need to put parentheses around it because that 9 is multiplied by everything on that top right. So it's multiplied by the R and it's multiplied by the 10. So I'm going to distribute on the right. So I have 11R equals 9R plus, and then 9 times 10 is 90. And now we're solving for R. So I'm going to subtract 9R from both sides. So 11 minus 9 is 2. So I get 2R equals 90. Then we divide both sides by 2. And R is equal to 45. So R is the number of Republicans. Now we need to go back to the question because the question says how many senators were Democrat and how many were Republicans. So we're not just looking for the number of Democrats or the number of Republicans. We're also looking for how many were Democrats. So we have to do more than just solve here like the other ones. All the other problems we had to basically solve here, and that was it. You know, your answer was your answer, but we're actually asking for two things here. So you have 45 Republicans, and then the Democrats are 10 more. So we have 55 Democrats. And we have 100 in the Senate, so you can even though that wasn't given in the problem, your knowledge about the government, that there are 100 senators, you can add those together and make sure that they add up to 100, and they do, so that is another check to make sure that you did your calculation correctly. Are there any questions? Okay. So these type with the proportion, these are pretty easy. They're pretty straightforward. It's just the hardest part is figuring out where the numbers go. And as long as you try to match things together, so like here we had Dems on top and Republicans on the bottom, as long as you try to match things together going straight across, it's sort of everything sort of falls into place. You just plug in your information and then you cross multiply. Now the examples are we start dealing with rates. These get more complicated, and these are the types of problems that people get tripped up on. This is like the famous type of problem that you would see on like a standardized test where you have a train going one speed and then another train leaves 2 hours later. When do they meet, or something like that? Like these are those types of problems. And people hate these types of problems, but they actually are useful. Because it gives you a different way to think about the problem, but also these types of problems where you're using rates, like I said, they actually are used with machinery to try to figure out how long it's going to take you to complete a job based off of different machines working at different speeds. So it actually is useful. So I'm going to start with just the distance one, so the uniform motion, where you're going to be using D equals RT. So we'll do several types of these. And then we'll move into the ones where you're doing rate of work, where it's a little more open-ended. So when you're having problems like this, where you're comparing two things that are going a certain distance, the setups are actually pretty simple, and understanding the setup is you're writing a proportion. And so it's very similar to the first ones we've been doing. So a motorist travels 80 miles while driving in a bad rainstorm. In sunny weather, the motorist drives 20 miles per hour faster and covers 120 miles in the same amount of time. Find the speed of the motorist in the rainstorm and the speed in sunny weather. So the key here is that you're doing things in the same amount of time. So I've got on the left in yellow the sort of setup. You're using D equals RT. And if we have D equals RT and we divided both sides by R to solve for T, we get D over R equals T. So since we've got two situations going on, but they do this in the same amount of time, you can set your times equal to each other. And that's how we get D over R equal to D over R, is because the times are equal. So then if you just replace T with D over R, then you have your distance over rate equal. And I have a subscript just for, because we've got two different situations. We've got the rainstorm and then sunny weather. So you're just comparing two different situations together, but you're still setting up a proportion. So we would have 80 miles and we don't know the speed. So we could just use kind of R here, unknown speed. We don't know how fast the motorist was going in 80 miles. Now in sunny weather, the motorist drives 20 miles per hour faster and covers 120 miles. So I could put 120 on top because we're having our distances on top. And I don't know the speed in sunny weather, but I know it's 20 miles faster than the speed in sunny or in rainstorm. So that's going to be R plus 20. So we've got our unknown speed in the rainstorm, which I'm just going to call R for the rate. And then it was 20 miles per hour faster in sunny. So I can express that as R plus 20. So I've got a proportion here, but it's a little more complicated than our other proportion because now we've got two denominators that contain variables. We still have to consider that the denominator cannot be 0. So R cannot equal to 0. And then here, R plus 20 cannot equal to 0. Because the denominator cannot equal 0. So if I solve R plus 20, this tells me that the rate cannot equal negative 20, which is no problem because we're not going to go in negative speed. So the equation, if we got a negative number for our speed, that would be a problem because we don't have negative speed. But just in regards to our equation, we can't get a speed of 0, and we can't get a speed of negative 20, or it causes problems in the actual equation. So once you've got this set up, then we're going to just solve it like every other proportion, where we're going to multiply diagonals. So I'm going to have 120 times R, and then 80 times R plus 20. And you want to make sure you remember those parentheses because you've got multiple things that you're multiplying it by. So I'm going to distribute on the right. So 80 times R, and then 80 times 20 should give me 1600. I did it on my calculator just to double check my math. We get 1600. So I'm solving for R. So I'm going to subtract the 80R from both sides. So 120 minus 80 is 40. So we get 40R equals 1600. And then I'm going to divide both sides by 40. And I get 40. So we have to go back to what they're telling us to find. It says find the speed of the motorist in the rainstorm and the speed in sunny weather. This 40 is the rainstorm speed because the way we set up our equation is that we had the rain on the left and then the sun on the right. So for the rain, R was our speed. So we've got 40 miles per hour in rain. And then the sun is R plus 20. So that means 60 miles per hour in sun. So you're taking that equation that you set up and you're reading the information from it, understanding that the top is the distance and then the bottom is the speed. So once you know that the bottom of these fractions are speed, once you know R, you can plug them in and then that tells you what your speeds are. Are there any questions? Okay. Now this is another distance equals rate times time, but this one's slightly different. Celeste walked 140 feet on a moving walkway at the airport. Then she walked on the ground for 100 feet. She travels 2 feet per second faster on the walkway than she does on the ground. if the time it takes her to travel the total distance of 240 feet is 40 seconds, how fast does Celeste travel on and off the moving walkway? So what makes this difference from the previous problem is that in the previous problem we had the same time. So they traveled the same amount of time, and so we can set those equal to each other because the time was the same. Here, we're not looking at the same amount of time. Like I can draw a picture here. We've got the people mover. Usually got some sort of railings there. That's the people mover. And then she walked on the regular floor. So she did 100 feet here, or 140 feet on the people mover, 100 feet off the people mover. And so we're adding these together because we're looking at a total that were traveled. So we're also looking at total time here because we're given the total time to travel is 40 seconds. So when you're finding in total, we're adding here. So this is a different type of equation because now we're adding our information together. So I have the setup here, total time, your T total. That means your time for the whole total. So the whole total here is 40 seconds. And because all the other times are in seconds, we don't have to do any unit conversions here. So I'm going to have 40 equals. And then we have two fractions, one for each portion. We have a fraction for the people mover and then the fraction when she's off of it. So for the people mover, she's on it for 140 feet. So it's distance over rate, again, coming from that D equals RT. And we don't know the speed that she's on the people mover, but we know that it's 2 feet per second faster than on the ground. So I'm going to add 2 to that because it's faster than when she's just on regular ground. Then she's on regular ground and she traveled on that for 100 feet and that was at some speed. So I had to add the 2 to the people mover portion because that's the one that's faster. So I had to put +2 on the first fraction versus the second fraction here. But you can see that this is a different setup because we don't have a proportion anymore. And so the way that we used to solve this one is different. So first we do need to just double check our denominators. R cannot be 0. And this denominator is telling that R plus 2 cannot be equal to 0, which if you solve, R cannot equal -2. Totally fine. We can't have a negative rate anyway. Now I'm going to add an extra blank slide after this because I have a feeling that I'm going to run out of space here. So let me just get that in there. Okay. So we've got our equation 40 equals 140 over R plus 2 plus 100 over R. So to solve this, we need to first figure out what the common denominator is. Well, you would factor, but these are already simplified. We don't need to do any factoring here. So we need to find out the common denominator or the LCD. And that is basically the combination of all the denominators that you have. So it's going to be R plus 2 and R. Because we can't remove anything from the denominator, we can only build it up. So if one of the denominators has an R, we need to have an R. And if one of them has an R plus 2, we need to have an R plus 2. We can't just add 2 to a denominator because we can't add to get a common denominator, we have to multiply. So that's why I have to multiply these together. So that is going to be our common denominator. So when you solve these, you multiply both sides of the equation by that denominator. So I'm going to rewrite what we have. And then I'm going to put in that multiplication. So I'm multiplying the left side by R times R plus 2. And then I'm also multiplying the right side by r and r plus 2. So we're multiplying both sides of the equation by that denominator. Now it looks messy here because it's just, you know, you've got a lot of stuff going on, so you have to be very careful about what you do and writing everything correctly. So one thing that I actually think is a lot easier to do, so this is what the book is saying to do, is to find the common denominator, multiply both sides by that common denominator. What I think is a lot easier is, instead of doing that, you still have to find your common denominator, but I would build your existing fractions up to that. So like my first fraction, I need to multiply it by the r. And then my second fraction here, I need to multiply it by the r plus 2. So I would do this, I would build the fractions to have the common denominator before I try to do this little multiply both sides thing. Because I think it's a lot, you're less likely to make a mistake when you do this. So I'm going to move to my next slide. I'm going to write what this multiplication is going to look like. And we do have to distribute on that second fraction. We'd have to do the 100 times r and 100 times 2. So when we do it this way, I think I accidentally grabbed the wrong color. There we go. We've still got 40 on the left. Now the first fraction, I'm going to have 140r over r times r plus 2 plus, and then on the right, I'm going to distribute the 100 through the parentheses. So 100 times r and 100 times 2. So that gives me 100r plus 200 over r times r plus 2. So we've got a common denominator, and now let's actually combine these together. And this does take more steps doing it this way, but you are less likely to make mistakes. So that is why I'm showing this versus the steps that the textbook gives. So when I combine them, I can put them in a single fraction. And then I can add my like terms. So I can do the 140 plus 100. So that will give me 240r plus 200 over r times r plus 2. And then once I'm in this place where I have a single fraction into multiple instead of multiple fractions, here is where I would multiply both sides, because you're a lot less likely to make a mistake here. So I'm just going to multiply both sides by the denominator. And that will allow us to just cancel out the denominator there on the right. So I have 40r times r plus 2 equals 240r plus 200. So I multiply both sides, it eliminates that fraction. Now on the left, I need to distribute here, and I'm going to end up with a quadratic. So this is why you had to learn how to solve quadratic equations, because you get something like this, you're going to end up with a quadratic. We're going to have to factor. It's a long process. I will admit, this is a long process to solve this problem. But this is the type of problems that you might see if you're working at some sort of place where you have things that are going at different speeds and you need to figure out how long it takes to do something. So this is something that you may see, specifically those that are maybe if you're in a business and you're doing business management, you may have to be managing something, and that involves different rates. Some engineers, you may be working with different equipment that does things at different speeds. So the engineering people, you may encounter this as well. So it is long, but it's important. So I'm going to distribute on the left. 40r times r gets me 40r squared. Then 40r times 2 is 80r. And this equals 240r plus 200. As soon as you see that you have a quadratic equation, you have that x squared, you have to get everything on one side. So I'm going to subtract 240r from both sides. And then I'm also going to subtract the 200 from both sides. I'm going to just kind of write it up there. But I like to do those in one step, but you can do those in multiple steps. So I get 40r squared. Then we have 80r minus 240r. That's minus 160r. And then I have minus 200 equals 0. So I have a quadratic equation, and I'm going to just kind of move to the right here to continue. So we've got some pretty big numbers here, and you're going to want to factor if possible. If I can divide 40 out of all of these numbers, that's fantastic. So I know I can divide 40 out of 40. I can divide 40 out of 160, and I can divide 40 out of 200. So I'm going to factor out a 40, and that's going to be my greatest common factor. And that leaves me r squared minus 4r minus 5 equals 0. So I'm solving this quadratic equation. I need to factor the r squared minus 4r minus 5. So this does factor, otherwise you could use the quadratic formula. This factors to r minus 5, r plus 1. I'm not going to go through the factoring because this problem is long enough. So if you need to fill in that factoring, if you still need to practice factoring, you can do that after this session to double check that you know what those steps are. But I'm just doing the factoring because, you know, this is already a long problem. So once you have your quadratic and it's factored and it's equal to 0, then we solve by setting each of these numbers equal to 0. So each of the factors. I don't have to do 40 because 40 equals 0 means nothing. So I have r minus 5 equal to 0, r plus 1 equal to 0. And then I solve each of these for r. So I'm just going to kind of do them both at the same time. I get r equals 5 and r equals -1. So we got two answers, but this is a real problem and we need to think about what makes sense. R stands for the speed. We have a positive number 5. This is feet per second, but we also got a negative. That negative doesn't make sense because you can't go a negative speed. So we can rule out the -1 as one of the answers because it just doesn't make sense. So that means our answer actually is 5 here for r. So we need to go back to our original problem to figure out what was r. So r here, that was for our walking speed. And that was off the people walker thing or people mover. I don't know what you guys call it, but that's what I grew up calling it. Because that was with that r went with the 100 feet. So that means that she walks 5 miles per hour when she's not on the people mover. The people mover was 2 miles per hour more, so that means she walks 7, or I keep saying miles per hour, that's fast, feet per second. I gotta make sure I've got my units here. These are feet per second. So she walks 5 feet per second off the people mover and 7 feet per second on the people mover. So I need to make sure that I put that here. So 5, and we want to make sure we use the units, 5 feet per second off the people mover or the walkway. and then faster on the people movers, and that was by 2 feet per second, so 7 feet per second on the people mover. And you should double check that you didn't get your numbers that like you weren't allowed to have. We weren't allowed to get a 0 or -2. We didn't get either of those. Are there any questions? Okay. Next one here. This is a little tricky. This is one that you have to think about. And so I'm going to go through how the little trick to this. It's not like that's not a trick question. You just have to do a little more thinking here. So a bus leaves a terminal at 9 o'clock. A car leaves 1 hour later and averages 10 miles per hour faster than the bus. If the car overtakes the bus after 200 miles, find the average speed of the bus and the average speed of the car. So I'm going to draw a picture here because I like to draw pictures whenever I have these kind of things. So I've got my little bus terminal thing, and we've got that's our bus. So this distance is 200 miles. From the bus terminal, the bus has gone 200 miles, because it says the car overtakes the bus. So the car meets the bus. I'm not that great at drawing cars, but the car, if it overtakes the bus, that means it caught up to the bus. So it also went 200 miles, but it did so, it left later and it traveled faster. So if I have the time, so let's say the bus, we don't know the speed of the bus, we don't know the speed of the bus or the time of the bus, so we can just call it, let's use R and then T for the bus. R for the speed of the bus, T for the time that the bus took to travel that 200 miles. So the car, the speed was 10 miles per hour faster, so I can add 10 to whatever the bus was. And then if you leave 1 hour later, you've actually spent 1 less hour on the road. So you have T minus 1. So we've got these two equations going on here. So the one thing that we know is that they went the same distance. So the distance of one equals the distance of the other. Now I'm going to just set up these two equations because we know that they went 200 miles. So 200 would be R times T. And the car also went 200, so let me do that in green. And that is the rate R plus 10 times T minus 1. So we have two equations here. And the book tries to set up this sort of thing with a table, but I've never really understood the table when I do these types of problems. So I don't use the table. I look at it this way. So the most complicated of these two equations that I wrote is the second one, the one in green, because it's got an R plus 10, it's got a T minus 1. So I'm going to take the one in blue and solve it for one of the variables, either for T or for R. Now we're looking for the speed, so I want to get rid of T. So I'm going to take that first equation in blue for the bus and solve for T. So instead of having 200 equals RT, if I divide both sides by R, I get 200 divided by R equals T. Then I'm going to take my second equation and replace t with what I just wrote. So where I see t, I'm going to replace it with this 200 over r. And that way we can get rid of the time because we're looking for speed. And then we have only one variable. So I'm going to have 200 equals r plus 10. And then instead of t, I have 200 over r and then minus 1. So you can see that this is a rational equation. We've got a variable in the denominator, but it is going to be a little tricky. So, and once again, I need to add myself another picture here because I am not going to have enough space, or I have to add another blank slide. So we need to multiply or distribute here on the right. We need to basically go through FOIL. So on the left, I still have 200. Now, if I do FOIL, I have r times 200 over r. So that will give me 200 r over r. And you'll see those r's are going to cancel out. So that's going to be nice. That's just going to give us a whole number here. So FOIL, now I need to do the outsides. R times -1, so that's going to be minus r. Then I have 10 times 200r, or 200 over r. So you do 10 times 200, which is 2,000 over r. And then 10 times -1, so that's going to be -10. So if we simplify what we have, I've got 200 equals, my r's canceled. I have 200 again. Then I have minus r plus 2,000 over r, then minus 10. So I'm going to add my like terms on the right with the 200 minus 10. So I have 200. 200 minus 10 is 190 minus r plus 2,000 over r. So I'm going to rewrite this equation on my next slide, and I'm going to show you what we're going to do to get rid of that r in the denominator. So, and hopefully, I know it's already basically 7 o'clock. If you're willing to stay on longer, I hope you do. So we have 200 equals 190. Let me make sure I've got minus r plus 2,000 over r. So to get rid of that r in the denominator, we're going to multiply both sides by r, because I have only one fraction that I need to basically cancel out. So that denominator is r, so I just want to get rid of that. So I'm going to have 200r equals, and then I have to make sure I distribute. So I have to multiply the 190 by r. So that's 190r. I have a minus r times r, so it's going to be minus r squared. And then when I multiply the 2,000 over r by r, that's going to cancel, and I'm going to get plus 2,000. So we want to get everything all on one side. I like to have positive numbers for my r squareds. This is a quadratic. We're going to have to factor again. But I like to have positive. So I'm going to move everything to the right, or to the left, sorry. So I'm going to subtract the 190r. I'm going to add an r squared, and then I'm going to subtract 2,000, and that just puts everything on the left, and then I'm going to put it in the correct order so that we have r squared first, then 200 minus 190 is 10r, and then minus 2,000 equals 0. So now we've got this quadratic that we want to solve. And so I'm looking at this. This should factor. So I'm going to try to factor it. I know that it's r times r And I think I just double check on my calculator. Yes. So I'm going to have a minus 50. No, I'm going to have a plus 50 minus 40. So 50 times negative 40 gives me negative 2,000. 50 minus 40 gives me 10. So that factors. So I set each factor equal to 0. So we have r plus 50 equal to 0. R minus 40 equal to 0. And then I'm going to solve each of these for r. So minus 50 from both sides. And plus 40 from both sides. And we got r equals negative 50 and r equals 40. So r is a speed. A negative doesn't make sense. So I can immediately rule that number out. I need to double check that I haven't made any denominator 0. When we set up our fraction here, the only denominator had r, so we know that r cannot equal to 0. We didn't get 0. So that means our answer is r equals 40. So we need to figure out, well, what was r? R is the speed of the bus, because that's what I set up for my bus equation. So the bus was going 40 miles per hour, and then the car is 10 miles per hour faster according to my formula here. So the car is going 50 miles per hour. So that is our answer here. So the bus, 40 miles per hour for the bus, 50 miles per hour for the car. Now, if you're interested in seeing how the textbook set table, I recommend taking a look at it. Maybe that will make more sense to you. I just always have trouble setting it up with the table format for these particular problems, so that's why I did not do it that way. There are questions. Okay, so I haven't gone through all of my examples. I know that it's been an hour. So what I'm going to do is actually show you the setup for the next examples. So that way, at least you can try to solve them on your own, and then you can maybe email me and say, did I get this right? But the setup is the hardest part for these anyway. Once you have the setup, the solving part is generally not so bad. So I'm just going to cover the setup for the next examples. So one painter can paint a room in 6 hours. Another painter can paint the same room in 8 hours. How long would it take them working together? So this is the kind of stuff that you'd be using if you're managing a plant, or you're managing multiple machines, you're trying to get a certain job done, and they work all at different speeds. Or even if you have employees that work at different speeds when they're doing certain things. So these are considered rate of work problems, and you're basically saying your rate, which is something per time, is equal to their rates added, their individual rates added. So I have this set up here where you basically have a one represents the total job. So one job basically is what's on top. So if you're getting one job done over the total time for that job, that's equal to if one person does that one job in this many times, plus if this other person does the job in this other amount of time. So that is our basic setup. So we have 1 over the total time. So this question is asking for how long it would take if they're working together. So we don't know that. So that's your unknown, 1 over t. The book uses x, but I like to use t for time. And then this is 1 over how long one person can do it by himself. So one painter can do it in 6 hours, plus how long the other person can get it done, which would be in 8 hours. So that would be your setup. To solve something like this, you would be basically multiplying both sides by t, And the book does show this alternate formula, and this is actually what I do is I usually write it this alternate way, where your total is 1, and then you write it as sort of proportions. 1/6 times t plus 1/8 times t. And then all you need to do is multiply both sides by the common denominator for the numbers to get rid of your fractions, and it's a lot easier to solve. So these are actually not as bad as they look once you know how you set it up. So let's look at another one. One carpenter can complete a kitchen in 8 days. With the help of another carpenter, they can do the job together in 4 days. How long would it take the second carpenter if he worked alone? So same sort of setup here. 1 over the time total. We know the total time is 4 days. So that's going to be 1 over 4. The first carpenter can do it in 8 days. So that's going to be 1 over 8. Plus, and then we don't know how long it takes the second. So that's going to be our unknown variable t. And then once again, to solve this, you would multiply both sides by t or multiply it by 4 times 8 times t. You get a common denominator to solve this, and then you would solve for t. And these are honestly way easier than that car and bus one that we did. These are actually not bad to solve by themselves at all. You don't have to factor anything, no quadratics, you don't have to deal with anything. And then this last one, same sort of thing. We want to set this up. So Gus works twice as fast as Sid. Together they can dig a garden in 4 hours. How long would it take each person working alone? So we have the same sort of setup. So together is 4 hours. So it's going to be 1 over 4 equals, and then I'm going to just kind of label here. Let's say that this is going to be for Gus and this is Sid. Gus is twice as fast as Sid. So if Sid is some unknown t, Gus is going to be 2t because it's twice as fast. So that's going to be 2 times t. So that's how you would set this one up, and then they total it take 4 hours. This one, when you solve, will give you a quadratic because you have to multiply both sides by, actually, no, you wouldn't have to just multiply by t because they both have t. Yeah, you're not going to get a quadratic with this because you don't have to multiply by 2t squared. You just have to multiply by something with the t, will cancel them out. So again, this one's not going to be too bad to solve. You just have to multiply by the common denominator or get a common denominator first to cancel out all your fractions. So sorry that I ran out of time. Too many examples here, but these last 3, which are the rate of work, once you know how you set them up, they're really not bad at all. And they're a lot easier to solve compared to the quadratic ones that we were doing here that involve a lot more work. So because they're not going to be quadratic at all. So these two, you know, the ones where you have to add things together here, those tend to be harder except when you have those rate of work because it's sort of just 1 over something.